In the last section of this unit, we're going to revisit double angle identities and verifying identities. So not just using identities to evaluate, get answers, but also to verify, to prove. Remember that in a proof, your answer is every single step, so you have to show it extremely clearly, and I need you to show each side of the equal sign in every step. Very important, in my opinion. My strategy is to usually expand whatever the double angle is and try to make it look like the other side. It's usually easier to turn a double angle into its formula than turn some formula that you're not as familiar with into a double angle. Also, our job is to only touch one side of the identity. I'm not giving you identities that you are required to use both sides. So you are actually required to only touch one side of the identity in order to get full credit. So the left side will remain secant squared x minus 2 cosine squared x. And you will write that in every single step and the same thing over and over and over. It's very important that it's organized and that I can follow your work super easily. Okay, that's what a proof is. Negative cosine 2x. So there's going to be a negative, and then we're going to replace cosine 2x. For cosine double angles, we have 3 options. So that one's kind of the tricky one to figure out when to use which one. Let's look at the left side of the proof, and we have a negative 2 cosine squared x over here that's not on the left, that's not on the right side. Well, I see a formula that includes 2 cosine squared x. So let's try substituting cosine 2x with that expression. 2 cosine squared x minus 1 plus tangent squared x. Now I notice that tangent squared x is on the right side, but secant squared x is on the left side. There's actually a Pythagorean identity, so I'm going to change tangent squared x. So if tangent squared x plus 1 equals secant squared x, if we were to subtract 1 on both sides, we would get tangent squared x is equal to secant squared x minus 1. And that's what we will replace the tangent squared with. Secant squared x minus 1. I don't need to put parentheses because it's not being subtracted. So we're going to distribute the negative on the right side. Cosine squared x plus 1 plus secant squared x minus 1. And now it looks like we're actually almost done. We just need to combine like terms and rearrange. So you have a secant squared x, a negative 2 cosine squared x, and 1 minus 1 ends up subtracting to 0. So we're done. Let's try this one. Again, I'm going to expand the double angle. It's not a surefire way to be the easiest, but that's kind of my method for now. So the left side will not be touched at all. We will just write it as it is in every single step. But the right side, we have 1 plus, now I'm not exactly sure which cosine formula to use, so I'm going to look around this and see that there's a positive 1 and a negative cosine squared x. Here we have a negative 1 and a 2 cosine squared x. That looks like if I use, the same one that I used last time. So I'm going to use the same one we'd used before, although you can very easily use the first one. 1 plus 2 cosine squared x minus 1 minus cosine squared x. Do you see how many things will simplify? We have sine squared x over tan squared x equals 1 minus 1 is 0. 2 cosine squared x minus 1 cosine squared x is 1 cosine squared x. Now this would be where it would be nice and convenient to be able to touch the left side, but again, we're not touching the left side. We're only touching one side, and we've already started with the right side. So our next step would be to get something that looks like it has sine or tangent in it. What I'm going to do to help me visualize what I need to put on the right side to make it look like the left side is I'm going to simplify the left side just for my own records to figure out what's going on. So you have sine squared x being divided by tan squared x. So I'm going to change that to multiplication of cotangent squared x. Sine squared x times cotangent is cosine squared x over sine squared x. So yes, if we were able to touch the left side, it would be much simpler. Mathematically, you are allowed to touch both sides, but for my class, for this test, I want you to do it only touching one side. So what we have here is an extra sine squared x over sine squared x that was being multiplied, and that's how we could, and when we reduced that, then we got cosine squared x. So we're going to do the opposite. We're going to actually multiply that in. It looks like cosine squared x needs to be multiplied by sine squared x over sine squared x. And this is a completely okay thing to do in an identity, is to just multiply by a special form of the number 1. The left side is going to stay the same, and the right side will be, I'm going to rewrite as sine squared x times cosine squared x over sine squared x. I want to turn this into cotangent, which is 1 over tangent, and then I'll be done. Times cotangent squared x. Cotangent squared x is 1 over tangent squared x. And now we have sine squared x over tangent squared x. That is the entire proof, is all of these steps, okay? So don't box in the last step. That doesn't actually make sense for a proof, because a proof is every single step is part of your answer. So sometimes playing around with the other side of the equation can help you know how to get to your destination. I'm going to expand anything that has a double angle, so cosine 2x I see again here. And next to it I see a 2 sine squared x. So I think I'm going to replace cosine 2x with the identity that has 2 sine squared x in it. I believe there is a double angle identity for cosine that involves that. Okay, this one, 1 minus 2 sine squared x. So plus 1 minus 2 cosine, 1 minus 2 sine squared x equals sine squared x over cosine squared x. 2 sine squared x minus 2 sine squared x, that's 0. Tangent squared x over 1. This one's so much easier, yay! Tangent squared x over 1 is just sine squared x over cosine squared x, quotient identity, and you're done. Our last one. Woo! So the double angle things are here and here. There's only one option for sine, so let's plug in that one first, and maybe that will help me kind of know what I want to plug in, which one I want to plug in for cosine 2x. So sine 2x is 2 sine x cosine x. No matter what, we'll still be subtracting this 1, and then we'll be subtracting whatever we're taking cosine 2x, whichever formula we use. and write down the right side of the equation every single time, untouched, every time. I would like to use a formula that gets rid of this 1 because it appears as though the right side has a product. If you distributed that in, that would have 2 terms, but right now we have way too many terms going on. So we want to get rid of this 1. It's a negative 1 minus, we're going to need to use the formula that has a minus 1 in it so that when we distribute the negative, it will be positive 1. Let's distribute the left side. 2 sine x cosine x minus 1. Distribute this. Negative 2 cosine squared x plus 1. At this point, we have a negative 1 and a positive 1. That becomes 0, so you have 2 sine x cosine x minus 2 cosine squared x. Almost there. Now, we need to factor out our common term, which is 2 cosine x, just like it is factored over here. 2 cosine x times sine x minus cosine x. And we did it.